the spectra or the spectral series of hydrogen atom uh, was observed by Balmer, and he named them different series as per the wave numbers. Wave number means that if we have nu bar, that is 1 by lambda, and this nu bar 1 by lambda was equal to RH 1 by n1 square minus 1 by n2 square, where n1 n2 these were the integers actually, and these are just integers at that time. They were not found to be what they exactly mean physically. Later on, when Bohr worked on this, Bohr was actually working in the Rutherford's lab, because Rutherford's model has some limitations, and he tried to look out those limitations. So when he tried to look out those limitations, he postulated some statements actually. So he made some postulates regarding the spectrum, regarding the various parameters of hydrogen atom or the spectra which arises from hydrogen atom. So before this, those postulates, let me remind you that we have seen this formula. This was given by the Balmer, and when we change n1 and n2 values, for example, when we have nu bar equal to RH, 1 by n1 is 1 square minus 1 by n square n2 square. So this will be Lyman series. This was actually Lyman series. So this is actually n1 minus n2, and we have the nu bar is RH, and it is 1 by 3 square minus 1 by n2 square. This varies n2 actually. This was Boston series, and here n2 is equal to 4, 5, 6, and 7, and here it is 2, 3, 4. Nu bar when it is equal to RH, and it is 1 by 4, 1 by, so it gives us bracket series. What physically this means, we will later on verify it, and we will see from Bohr's theory how it is explained there. And it is RH is 1 by 5 square minus 1 by n2 square. Some books write it as n simply here, but don't worry, it is just a representation. So it is 6, 7, 8. So this is 5, 6, 7. So this was a p-point series, and for n equal to 2, it was a Balmer series actually, when we have n1 equal to 2. So this is how the different series were named at that time, and similar regularities, there were some similar regularities. That means the pattern was observed in other elements as well, in other atoms, more complex atoms. And structure for that series or formula for those complex atoms is almost same. We will not go into those details. And so let us now move into Bohr's theory. So before Bohr calculated the energy, radius, or velocity of an electron in the Bohr orbit, in the first orbit, or he calculated the radius of the first orbit of the hydrogen atom, or hydrogen-like atoms. Hydrogen-like means helium 1 plus, lithium 2 plus, like these, which have one electron in the last shell. So Bohr, actually, he postulated first, then he derived actually various parameters. So there are Bohr's postulates, and he proposed these. He worked on these postulates actually. He designed this theory around 1913 in Rutherford's lab. And he combined what he does, what was the basis for his postulates, or what were the basis for his theory. It is a semi-classical theory actually. Neither it is a fully classical theory, or neither is a fully quantum mechanical theory. Classical in the sense that from Rutherford's model, we know that we have a classical orbits, paths around the nucleus in which electron revolves, and quantum mechanically that It is not exactly that particular path which is defined there. It is a probability in terms of quantum mechanics. It was not neither fully quantum mechanics and neither fully classical mechanics. Somehow he mixed both of these. From quantum mechanics, he considered the quantization rules. Quantization means he used the concept of quantization of energy, and he used the concept of quantization of angular momentum. These two. And from classical theory, he used those classical orbits which are around the nucleus. Those were called as stationary orbits as well, and they were stable according to Bohr. So, and from quantum mechanics, he used one more thing which was important from Einstein's photoelectric effect, that was photon, where we found that electromagnetic radiation is quantized, and the basic quanta for that is photon. So somehow he combined all these different aspects of both classical theory as well as quantum mechanical theory, quantum mechanics, and postulated a theory and postulated some statements regarding the understanding of the structure of the atom or hydrogen-like atoms. If somebody has any issues in understanding, please let me know, and we will have we will repeat it again. So what he does, sorry, what Bohr has designed is that so Bohr used the concept of nuclear atomic model, number one. Number second was the Planck's quantum hypothesis regarding quantization of energy. Number second was the Einstein's concept of photon to explain the observed line spectrum. Actually, the main aim was to how to observe where from these line spectra originate and how it originates. Because this was one of the main drawbacks of the Rutherford's theory, or up to the theories till Bohr worked, including that of Rutherford. So Rutherford's theory has a drawback that it was not able to explain that line spectra actually, and Bohr worked to explain that. So there are postulates. There are some books write it as 2, 3, some write as 4, but they combine two of the statements in one, and some write them as separate. So it is not that much a big issue. The first postulate which Bohr said and the Bohr proposed while explaining line spectra of hydrogen atom was that an electron in atom moves in a circular orbit. An electron in atom moves in a circular orbit under the influence of Coulombic attraction between the nucleus and the electrons. So this was the first postulate according to the law of classical mechanics, and this was one of the classical mechanics laws. So first postulate was that electron in an atom moves in a circular orbit, and he gave them a particular name, those orbits, and these were called as stationary orbits or stationary paths for those electrons. And he proposed that the electrons move under the influence of Coulombic attraction between the electron and the nucleus. That means if we have a nucleus here, it is a positively charged. We have here some paths outside. If electrons are moving in these orbits, there's a force of attraction between these nucleus and the negatively charged electrons. So this is Q1, Q2. Then you find force of attraction from the Coulomb's law, Q1, Q2 by 4 pi epsilon naught R square. So he used this concept, Bohr, in first postulate, and said that the force of attraction between the electron and the nucleus, according to the classical mechanics, was from it. This idea came from the classical mechanics. And the initial idea is that there is a nucleus which was proposed by Rutherford. So he used the concepts from the Rutherford's model of that nuclear atom, nuclear atom. The second postulate was, this was the first. The second postulate was there are various large infinite number of orbits. There are the word term orbits was used actually. The Bohr postulate said that okay that there are infinite number of orbits which are there outside the atom for the electrons, the infinite number of orbits which would be possible in classical mechanics. So according to classical mechanics and Bohr, he proposed that there may be infinite number of orbits which are possible, and it is only possible for an electron despite of being infinite number. But for an electron it is not possible to move in every orbit. It will move in an orbit for which it is orbital angular momentum L is an integral multiple of h by 2 pi. So he said that uh, electron will move in only that particular orbit
सर ये पॉइंट फिर से इलाबरेट कीजिए
मैं कर रहा हूँ that electron will move only in that particular orbit for which it is angular momentum, orbital angular momentum generally orbital angular momentum L is equal to n times h by 2 pi. This is the integer, n is a positive integer. So it is integral multiple of the orbital angular momentum of an electron. So for which that means if electron moves in any orbit, for example, suppose that in the orbit first n equal to 1, so it is orbital angular momentum will be h cut. Simple. If it moves in second orbit, it will be 2h cut, 2h by pi, h by 2 pi. So Bohr proposed that out of infinite number of orbits which are there for the electron outside the nucleus, only those orbits are allowed for which the orbital angular momentum of electron L is integral multiple of h cut, where h is the Planck's constant. We know that. So we can say that this mod of L, and it is a vector quantity, so it is nh by 2 pi, and n is equal to 1, 2, 3. Yes. So here is the quantization actually, the concept of the quantization of orbital angular momentum of the atomic electron. And from here, the quantization of energy came, a concept came actually. So that means we use this n here from here, and this n is also used in the energy derivations when we derive the energy expression. So what is the second postulate? The second postulate what about the quantization of the orbital angular momentum. That means electron can move only in that orbit for which its angular momentum is integral multiple of h by 2 pi. The third one is that since we from the Rutherford's theory we saw that electron moves continuously in an orbit, circular orbit, but the drawback was that if electron moves continuously, it should move and radiate that energy what it has gained. A time will reach when electrons will collapse to nucleus and the atom will not exist, but that is not true. That is contradictory what we see, what we observe. So what in that response to that response, what Bohr proposed, he proposed that in spite of accelerated motion, since it is continuously moving a charged center here, yeah, so it is moved this charged center here. When it moves, so electron goes here, it will be accelerated because of this, according to classical theories, Rutherford's or earlier theories. But by then, according to those theories, the electron will accelerate and it will radiate an energy. When it radiates energy, at the time will reach when it will have no energy and it will fall directly to nucleus. The nucleus is a positively charged, so it will collapse to that. It will be attracted that. But what Bohr proposed that it is not true, but in spite of its accelerated motion, if it is an accelerated motion, it does not electromagnetic energy while moving in an allowed orbit. So those orbits where electron will move are called as allowed orbits. And in those allowed orbits, no energy will be radiated if it is moving in that orbit. For example, if electron makes an if electron is moving in this particular orbit, then it will not radiate any energy when it is in this particular orbit. What happens when it is not in this orbit, moves from another one orbit to another, that is another question, that is other concept. But when it is moving in only a single orbit, when it is not moving in any, it is not shifting from one point to another point, when it is a circular path which is fixed, then it will not radiate any energy in an allowed orbit. So those electrons will only move in allowed orbits. And what are the allowed orbits? For which L is an integral multiple of h by 2 pi. No emission of radiation in allowed orbit. That means when electron is moving in allowed orbit, that means the total energy remains constant. It remains stationary, conserved. The fourth one is, there is actually these 3 and 4th are some in some books it is combined actually, but here we will not combine it. Let us do it separately. So when an radiation
Sir,
is,
ये क्या है? Radiation is allowed orbit.
no emission of radiation in allowed orbit is nahi hai, in allowed orbit. Allowed orbit means that, for example, if this is a nucleus, we have an orbit outside this, an electron is moving in this. According to Bohr, it has a particular path for traveling, for path to move, which Bohr named.
It means radiation is only possible when there is transition.
Yeah, that is what we are going to see in fourth statement, the fourth postulate.
Yes.
Up to now, there is no transition as it is, as the atom does not make any transition, or it is not excited by some external forces. So unless and otherwise it is influenced by some other forces, there may be a transition. There is a transition. There may not be, depending upon the energy. And but in a particular allowed orbit, if electron is moving in that allowed orbit, which Bohr called as allowed orbit or stationary orbit, there is no emission of electromagnetic radiation. This is what Bohr postulated in this third postulate. Now, the fourth one, which is important, all are important actually, but in respect to the third, you can understand from from this third and fourth, how does the line spectra originate actually.
So why it is called stationary?
Bohr named this because electrons' energy remains stationary. Energy does not change. Bohr named it as a stationary orbit because electrons' energy remains stationary. It does not change. It is in a particular fixed that path, which has a, because what is an orbit actually? It is a particular energy level.
Yes, sir.
It remains constant actually. That's why he give the name stationary actually.
It is constant in a particular orbit.
Yeah, he named those particular paths actually as orbits. He said that electron moves in a particular definite path, which is not the actual position which we know at present because of the modifications in the from the quantum theory. That is why I called it as that is the semi-classical theory. It is not a fully quantum mechanical theory. There are some ideas which were taken from the quantum mechanics, some ideas which are used from the earlier classical theory. So in postulate 4, Bohr said that, he proposed that electromagnetic radiation is emitted if an electron makes a transition actually. That means electromagnetic radiation is emitted. In the third one, we said that there is no emission if it is in a particular orbital path, but then when is it emitted? So according to Bohr, the electromagnetic radiation is emitted if an electron which is moving in a particular initial energy state EI. For example, if an electron is moving in an EI energy state, initial EI energy state, and discontinuously changes its motion, discontinuously. That means it was particularly moving like this, and suddenly it jumped to some point discontinuously. It was having an initial position here, and it move to some final position EF. So what does initial here mean? Remember that, don't confuse it with the earlier concepts in actually emission. Initial point, initial position. So according to Bohr, energy will be emitted or radiated if an electron changes its motion from initial energy state or initial energy EI, and it moves in a lower orbit of energy EF. So if this is the EI, according to Bohr, if it moves to EI, EF, sorry, here, then it will emit some electromagnetic radiation, H nu. So from the fourth postulate, we can understand that there is an emission of the electromagnetic radiation or the photon when there is a transition from the higher energy state to the lower energy state. And that higher energy state is in the initial state actually, or the emission. Because emission will only take place when it is makes a transition from higher energy state to the lower, then only the emission will take place. If it goes from this ground state, lower state energy to higher energy state, it will be absorption.
Yes. And this same amount of energy is absorbed.
Yeah, if it is, yes, same. If it is elastic collision, the same amount of energy is absorbed, and it is not always possible that same is absorbed and same is emitted. Sometimes it is possible that you can have a more energy absorbed but less emitted. It does not mean that energy
In
is,
elastic.
yeah, in elastic collision, and reasons may be different. And in case of Raman spectra, if you have studied, you have Stokes, anti-Stokes lines with higher frequency, lower frequency, higher energy, lower energy. There are some different reasons then. For time being, we assume that if everything goes as it is ideal case. So we assume that it for an ideal case to understand the things better. If we assume that it makes a transition from higher energy state, which we label as initial energy state, and makes a transition to the lower energy state, which makes as a final energy state, then there is an emission of an electromagnetic radiation. This is what Bohr proposed in the fourth postulate. And in the same way, the frequency of that emitted radiation, let us suppose that frequency is emitted as nu dash. Okay, and that is given by EI minus EF divided by H. There is a conclusion we can derive from Bohr's fourth postulate. That the frequency of the emitted radiation is given by I initial minus final divided with the Planck's constant H. Okay, so here these were the four postulates which were proposed by Bohr in explaining the structure of atom and the line spectra of a hydrogen atom actually. These all were used to explain the line spectra of the hydrogen atom. And there was a mix-up of the classical, non-classical physics, and your circular orbits is actually a classical concept. Non-classical was the quantization of orbital angular momentum. Non-classical was the use of photon as a quanta of the electromagnetic radiation. Then Bohr used these basic postulates and he derived the expressions then for energy of the orbit, radius of the orbit. Then we were able to derive the velocity of the electron in the particular orbit. So we will move and we will find the explanation of spectra of hydrogen-like atoms. What is the reason for how this arises, this spectra? Hydrogen-like atoms spectra arises. For that, we can also say that it is a explanation of hydrogen-like atoms. That means spectra which is derived from hydrogen-like atoms. It is there is some mathematics, there is some theory. So for that, let us consider that we consider a particular atom, It's a hydrogen-like atom, and let us suppose that it has a nucleus which has a plus Ze charges at the nucleus, and there is a circular orbit here. It's not may not be accurate, so you can assume it to be accurate. So for example, if we are is the orbit of radius r, and an electron is here which is revolving anti-clockwise, and its velocity vector is like this. Velocity, direction of velocity is this. Electron here, and this is the nucleus. This has plus Ze charge at the nucleus if it is a hydrogen-like atom like lithium 3 plus 2 plus, but the positive charges will be same. We are not reducing the positive charge, actually we are reducing the negative charge. And it has an electron of mass, and this atom has a mass m. For neutral hydrogen atom like Ze 1, for singly ionized helium atom that is 2, for doubly ionized lithium atom that is 3. Doubly ionized lithium atom, singly ionized helium atom, or neutral hydrogen, they all have Z equal to 1. This electron equal to 1 electron. We have 1 electron. We assume that the electron revolves in a circular orbit as proposed by the Bohr about the nucleus, and we initially also assume that nucleus is infinitely heavy compared to the electron, and nucleus remains fixed in space. Then when nucleus is heavy, so assumptions are there, nucleus infinite mass. आवाज आ रही है?
यस सर आ रही है.
कट क्या आ रही है? Just check your internet connection. Maybe मेरा internet connection भी weak हो सकता है. And okay, just check your network, and if not, then let me know again. आप मुझे दोबारा बता सकते हो अगर दोबारा नहीं आ रही हो क्या आवाज. So infinite mass and rest. Nucleus is of infinite mass, it is at rest. So these are it. Then we have a Coulombic force between the electron and the nucleus. Positive charge, negative charge, force of attraction is there. So that force will be 1 by 4 pi epsilon naught r square, and it is Ze of nucleus and E of electron. This is how we are electrostatic Coulomb force. I can write here Fc. We also have the centripetal force because of the rotation of along a circular path with respect to a particular fixed center. So we have a centripetal force which is Fce. I can write Ce here, mv square by r. This is all you have done actually in basic classes. I hope that. For a stable orbit, these two forces will be equal. For stability, one by 4 pi epsilon naught and Zee by r square is equal to mv square by r. This is for stability. So they will be equal and opposite, and that is how the electron will be in a stable orbital path. Here, Z is the nuclear charge, E is the electron charge, R is the distance between Z and E, which is actually a radius of orbit. V is the velocity of electron. M is mass of electron. Then what remains there? There are the constants. 4 pi epsilon is permittivity of the free space, and other terms, 4 pi is a constant. Now we know that since it is an orbital motion, it has an orbital angular momentum. What is that equal to? L mv into r. And according to Bohr's second postulate, Bohr's postulate, that is actually equal to n
NH by 2 pi,
by 2 pi,
NH cross.
n extra. And n is, while n is a positive integer, 1, 2, 3, and it's called a principal quantum number actually. This is what is actually the principal quantum number n. So from here it came. And from these two, we can find that from above equation, this, this will be first, let this be second. So from second, we can find the velocity of the electron in nth orbit, 2 pi mr. You can use this value if it is third. We will use this third in first to get radius of the orbit. So we have from first Z square will be 4 pi epsilon naught mv square r from the equation 1 here, this. So 1r and 1r will end up here, and we will, and this is used in first to be, this will be used in first, and from first we see that here Z square is 4 pi epsilon naught m or mv square r, and this is simply actually from this equation here, this equation. So you will get an idea. So this is Z square equal to 4 pi epsilon naught m square, and I can put up the values of, now here we will put up the value of v here, this from equation 3, and it is 4 pi epsilon naught mr and h by 2 pi mr square, and you will end up with this equation, n square h square divided by 4 pi square mr. r simply further, there will be some cancellation. It gives us r is equal to n square h square epsilon naught divided by pi m and z e square. So let this be 4. We can use this value of r in equation 3. Now what is 3? 3 is velocity of electron actually. We use value of r in expression for v, velocity of the electron in the orbit, in the nth orbit actually. This is the equation for the nth orbit, so remember that. And for an atom having atomic number z, so both are here, z and n. These are variables actually for nth orbit and for an atom having atomic number z. So we using value of r in expression for v, and we will find that v will be equal to z e square divided by 2 n h epsilon naught. Sorry, I will repeat it. There is some. It is z e square divided by 2 n h epsilon naught. Again, n is an integer. We can write 1, 2, 3, etc. Let this be 5. So almost half is done. We are left. There is now one more point is remained. That's energy. After now we have calculated the velocity. We have calculated the radius. Now the energy is left actually. If you see from there, the application of this angular momentum quantization condition, it will be, these restrict actually the possible circular orbits of a particular radius. That means the n actually nh by 2 pi r, n restricts the radius. So r is directly proportional to n square. From here, r is proportional to n square, where v does not depend upon n, it depends upon z only. Oh, sorry, it depends inversely on n. Sorry. And v is inversely proportional to n. For smallest orbit, what is smallest orbit?
सर हम 5 तक क्यों दे रहे हैं?
क्या बोल रहे हो?
5 सर, ये 5 मैक्सिमम लिमिट है इसका n का.
ये इक्वेशन 5 है.
ये इक्वेशन 5 है.
नंबर 5.
ये इक्वेशन 5 है. Sorry. No problem. ये इक्वेशन 5 है. Actually, I will put up a different color for that. So this is equation 5. Don't worry. Equation 5. So smallest orbit will be n equal to 1. So for n equal to 1 and for hydrogen z equal to 1, if you calculate the radius of the orbit r, that is approximately equal to 0.53 angstrom. And these are calculated by putting up the values of r equal to 1, z equal to 1, and h equal to 6.63 10 to power minus 34 joule second. Epsilon naught is 8.85 10 to power minus 12 coulomb square per Newton meter square. And then charge is 1.6 10 to power minus 19 coulombs. And putting up these constant values of the constants, you will find that r for the first orbit is 0.53 angstrom. This is actually a good agreement. This is in good agreement with the estimates made from other data. That means it is good agreement when people have with the value calculated from other theories, like such of one of them is kinetic theory of gases. Okay, people have calculated this value from the kinetic theory of gases, and it is in agreement with that value. The velocity of an electron for the smallest orbit, you can also calculate that, v. So v for smallest orbit, v for n equal to 1, that is the smallest orbit, is approximately equal to 2.18 into 10 to the power 6 meter per second for the first orbit. This is the velocity. And if you see closely this value with the speed of the light photon, most often we assume that electron moves with that speed, but if you see this speed for the first orbit n equal to 1, this is almost 1% of the velocity of light, less than 1% of the velocity of light. It is approximating 1 by 137th of c, the velocity of electron in first orbit, n equal to 1, and it is 1 by 137th of c. So here in this case we can ignore the relativistic effects according to Bohr's theory. But this is the case when z equal to 1, n equal to 1, but large values of z, for when you increase z, when z increases for very large value of electron velocity becomes relativistic. VR means relativistic. For large value of z, as we increase the z, it becomes relativistic. And there is one more concept why Bohr did not choose n equal to 0. So had he put n equal to 0, these equations would have, if you see here, we will have gone infinity here. This r will have gone simply 0. So, and because the relativistic effects were not taken into consideration by the Bohr, so he does not take n equal to 0 because we will have gone that and then infinite. Now we are left with the energy, actually, energy of the electrons in the orbit, given orbit, allowed orbit actually, or the stationary orbit as proposed by Bohr, that we will calculate. Let us suppose that electron is moving in any of the one of the allowed orbits. We define a potential energy of the electron to be 0. We calculate the energy from the potential energy first. We will calculate first potential energy, then kinetic energy.
ये आवाज कट के आ रही है सर,
कट के आ
कट
रही है?
आ रही है आवाज.
Wait,
Yes, sir.
wait, no problem. Okay, can you hear me?
Yes,
अभी ठीक है?
जी सर.
Okay, I have switched the network actually. So we calculate the potential. So how you define actually the potential? What is the potential actually? Or when we say that we need the object has a potential energy, we take any object, we move it from one point to another point against some force. Yes, if we increase z, there will be relativistic effects. Sure. Somebody asked the
Okay,
question if
sir.
it is z, is there's relativistic effects. So that is what I mean actually from that statement. For large value of z, the electron velocity becomes relativistic.
यहाँ पे लेकिन हमें नहीं लिखा कि हम Z
क्योंकि z is 1,
वन
it
ले
is
रहे हैं।
variable. Z is just 1 here.
Yes, sir.
Okay, sir.
We are calculating the value of V for
Yes,
Z
sir.
equal to 1.
Ji, sir.
For hydrogen atom.
Yeah, for hydrogen atom. Only and for that too in the first orbit, n
Okay,
equal
sir,
to
I
1.
got it.
Okay. So when we say that somebody has some object
sir,
or
thank
somebody has gained a potential energy. So we move an object against some force. Just understand that we move an object against some force and place it from one point to another point. It will gain an
Yes, sir.
energy because we have given that energy to that object for doing a work against the given force. For example, if I place a charge in an external electric field,
Yes, sir.
जो आपने 12th में पढ़ा होगा, it is a 12th standard concept. You bring in charge from some point and place it in some external electric field. The charge will have some gain in the potential energy because we have done some work on the charge against the electric field.
Yes.
Okay, that is how an energy, potential energy is gained by that charge. Similarly, if we assume that here an electron is, and we bring another electron from some infinity against the Coulombic force of the nucleus and the electron, or there is some force, we define the potential energy of electron to be 0 when electron is at infinity. First it is at infinity, distance from the nucleus. Then the potential energy U at a finite distance R. So if it was here, this is a nucleus, this is the path, here some at here, if suppose that here we are at infinity here, then U for it is 0 because there is no force from the nucleus at this point. So when I bring it here, so there is some energy because of that attraction. It will gain some energy in the Coulombic field of the nucleus as well. And then there is a potential energy U at a finite distance R, U. That is work done in moving the electron from R to infinity against the electrostatic force.
नहीं आ रही है, ये break
Sir,
हो रही है
आवाज
बहुत।
आ रही है।
तो ब्रेक हो रही है, आपकी आवाज मुझ तक साफ पहुंच रही है, दैट मींस जहां नेटवर्क तो ठीक है, ऐसे सबके साथ इशू आ रहा है कि
सर आपकी कट आ रही है। सर आपकी
हमें
बहुत कट आ
बहुत कट आ रही है.
रही है।
Don't know what the problem is. Let me see. Our internet connection is unstable. Hold on for a while. Okay, can you hear me?
Yes, sir.
Sohail?
Yes, sir.
Yes sir, yes sir.
Okay. जिसको इशू आ रहा था वो भी बोल सकते हैं कि आवाज आ रही है कि नहीं आ रही है ठीक से. So for example, electron was at a particular position R. We are here and we have electron here. So that electron is moved from this R to some infinity here. Here it has some potential energy. It is going to infinity again as the Coulomb field of the nucleus because nucleus will attract towards it itself. So we are doing work actually again as the force from the nucleus. So energy is gained by the electron when we move it at infinity. And that force of attraction at some distance from distance r, that is equal to -1 by 4 pi epsilon naught z square by r square. This simple Coulomb's law. Minus is because it's a force of attraction actually. For attraction we take minus, for repulsion we take plus. This is sign. And why? How do you use potential energy as the work done? It is F dot dr actually. It is F dot dr. That is potential energy. And we, if for a U is equal to integral of from r to infinity. We are moving from r to infinity. Again, is the Coulombic field. There's minus dr. Is it okay? And if you find it is equal to minus 1 by r times 1 by 4 pi epsilon naught z square. If you integrate that equation, above equation. If there's any confusion, please let me know. This is the simplest one. You can do it easily. Work done is actually force times displacement, how much displacement we are doing, and that work done is stored as a potential energy in the body, in the electron actually, and we calculate that u by the integral. Simple, because we are moving against some r is varying, so we have taken the integral actually. This is potential energy. Now kinetic energy. The kinetic energy is k. Let us suppose it is half of mv square, and from equation 1 is this is, let us suppose this is some equation 6, I think 5 we have given above. Let this be 6, this be 7, and from 1 z e square by r square is equal to mv square by r, and here 1 by 4 pi epsilon naught. यहाँ से आपको you can find the value of this v square from this equation. You put up the value of v square from this equation into here. So k is equal to 1 by half of m v square will be there, go z e square r divided by 4 pi epsilon naught r square into m. M and m will cancel, this r and 1 r will go, so k will be equal to 1 by 8 minus, I can write here, it is z e square 8 pi epsilon naught r. It is kinetic energy, so it will be positive. There is no need to write this minus, so they positive. Z 8 pi epsilon naught r. Total energy will be, it is u plus k, potential energy plus kinetic energy. Then how it is? It is z e square by 8 pi epsilon naught r minus z e square by so we have added up this equation and this 6. We have added the 6, 7, let this be 8. I put up the value of 8. So we added 7 and 8 because equation 7 is negative, that's why it's minus here, and we find it to be this way. If you put up the value of r from equation 4, we have value of r from equation 4, use that value of r here. Use value of r in 4, we find that the energy of the nth orbital, E, total energy of the nth orbit, it is equal to minus z square E4 8 epsilon naught square h square, and it is 1 by n square. R we have calculated above. I have put up the value of that r here, and this is r, here it is r, equation 4. This is equation 4 here. Here we have n here. You have to use this value in this equation, total energy equation, and you will find the energy for the nth orbit. Here it is n. And if you see that is, so as you move away from the nucleus, center of the atom, energy decreases as a square of the number orbital, as a square of the principal quantum number n. And this is the actually the quantization of the orbital angular momentum, and it leads to the quantization of the total energy, because it depends, it is now, these all are constants actually. Z, it is an integer, these all are integral values here, and this n is an integer. So it leads to the quantization of its total energy of the electron in an orbit. If you put up the values m, z, e, epsilon, h, and then change the value of n, you will find E1 for n equal to 1, lowest orbit. So according to this value, it is higher than other values. It will be large, and you will find E1, it is 13.6. It is an attractive, that is why it is minus here. And it is called as first ionization potential, or it is also called as sometimes binding energy of the hydrogen atom. First orbit, in the first orbit. It is minus 13.6 eV, which is approximately minus 21.7 10 power minus 19 joule. And 1 electron volt, you know what is 1.6 10 to power minus 19 joule. Similarly, if you calculate for E2, it is minus 5.42, which is minus 3.39. E3, it is minus 1 point. Then there is E4 for fourth orbit. Go on and you go on, it is minus 0.85 eV. This is 0.85 eV. And at infinity, it is 0, simply because it's inversely proportional to n from that. So energies are all negative actually. That means the electron is bound to the nucleus by the attractive Coulomb forces. Lowest energy, which is most negative. As you move away from this nucleus, the energy decreases negatively. It decreases with the negative sign bar. And when it approaches infinity, the energy goes to 0. And then electron will not be bound to the nucleus at infinity. It will be a free electron at that time. For n equal to 1, this is the ground state of the hydrogen atom. For n equal to 2, 3, 4 and higher states, these are called the excited states. That means E1 is labeled as ground state, E2 will be as E2, E3, E4 up to En, or if you go up to infinity, these will be excited states. Not the infinity, we cannot go up to actually infinity. These are excited states. So for hydrogen atom, the ground state E1, you find that it is, if you find that it is equal to actually called as Redberg 1RY E1. So it is a unit, actually energy unit of energy. We measure the energy of the electrons in different orbits in terms of the Redberg, how many Redbergs the electron energy is. And 1 Redberg is the energy which is attained by the electron for first orbit, n equal to 1 Bohr orbit, first Bohr orbit. And this 1 Ry is equal to me4 divided by 8 epsilon naught square h square. It is 21.7 10 to the power minus 19 joule, which is minus 13.6 eV. So if you want to remove an electron from first orbit n equal to 1, you have to provide minimum energy of 13.6 eV plus to remove that electron from that. That is the binding energy of the electron for in the hydrogen atom. And it's the ground state atom, ground state energy of that. Okay, there is more for today's lecture. I think we will stop here. And